We're going to look at the comparison between QC and KC. The problem statement says for the reaction hydrogen plus iodine goes to 2 hydrogen iodide. The equilibrium constant Kc is 160 at 227 degrees Celsius. That temperature keeps showing up. In which direction will the reaction go to reach equilibrium given the following sets of conditions? Okay, so just checking in with where we are. We said on the last homework problem, 1, that position of equilibrium depends on the value of Kc. Or a Kp, but typically we're going to do most of our problems involving Kcs and a small number of problems with Kp. So position of equilibrium depends on the value of Kc, and we just said if Kc was less than 1 times 10 to the minus 4, the position of equilibrium lies towards reactants. And if Kc, I didn't mention this, but I might as well, Kc greater than 1 times 10 to the plus 4, the position of equilibrium lies towards products. And if it falls between those two numbers, it typically is somewhere in the middle. Now let's talk about QC versus Kc. So Kc, as we've said, is the equilibrium constant. And the equilibrium constant is the ratio of concentrations at equilibrium. QC, on the other hand, is the same expression as Kc. Except and what will happen is you'll be given concentrations, and so same expression as Kc, except not at equilibrium. And I'll show you what I mean in a minute, but same expression as Kc except not at equilibrium. QC tells us how to get to equilibrium. Okay, and here's what I mean by that. So I can write out a QC expression, and it is exactly the same as Kc, meaning it's going to be products raised to coefficients divided by reactants raised to coefficients. And what I'm going to do now is I'm going to plug in the concentrations that I've been given, and it's going to look like this. So HI is 7.8 times 10 to the minus 2. Squared divided by each of my concentrations here. One 1.0 times 10 to the minus 4 times 1.0 times 10 to the minus 1. So these are the two concentrations in my problem statement. And if I do that, I get, well, let me multiply it out because I cannot do this in my head. 7.8 times 10 to the minus 2 squared divided by 1.0 times 10 to the minus 4 divided by 1 times 10 to the minus 1. I get 608. Is my QC. Now my KC in this problem is 160. And next what I have to do is I have to compare QC versus KC. QC is greater than KC, which means that the concentrations here in my products are larger than at equilibrium. Concentration of products are larger than at equilibrium. So, for this reaction to get to equilibrium, it has to turn some of the products back into reactants. That'll make this number smaller and these numbers bigger. So the reaction must go backwards to get to equilibrium. Reaction must go backwards to get to equilibrium. And when the reaction goes backwards, it converts products into reactants. Okay, that's what going backwards means. We know that reactions now, and this is the whole point of this chapter, reactions can go in the forward direction, reactions can go in the reverse direction. And what we're calling that, if we look at our answers now, so if we get to this point, so this is our process, we found QC, it was greater than KC. We have more products and not enough reactants, so we have to do our reaction backwards. And since backwards is to the left, this is called shift left to reactants. Shift left to reactants, and our answers are QC has no relationship with KC, shift into overdrive and hit the road. As much fun as it would be if that was the answer, that one's never the answer. QC is less than KC, no, reaction shifts right. That's not what we found. We found that QC was greater than KC, reaction shifts left towards reactants. That is the answer for this question. So QC is any given concentrations I give you, and that helps you figure out whether you have to go to the right, to the left, do the forward, do the reverse reaction to get to equilibrium.